Good evening. This is probably one of the more interesting, I think, or applicable topics that we're going to talk about through waves right now. When we get into a lot of this new stuff, actually, for the next couple of chapters here, pretty much from now to the end of the year, we'll really be looking at more like applications that they have to our modern life and to our daily life. There's a lot to do with pressure and Bernoulli's and that stuff with the effects in our daily life, but I think you're more used to seeing, especially with a lot of electronic stuff, a lot of the effects of, for example, in this video here, we're looking at the Doppler effect, which follows along in textbook section 16.9. You probably are familiar with a lot of, you've heard the term before, and you're probably a little more familiar with it than in some of the other cases. But either way, without further ado, let's begin. So, Doppler effect, starting in section 16.9, and here we go. The Doppler effect is a change in frequency of a wave or of an oscillation, or a wave or a disturbance due to a moving either observer or emitter. So whether it can be a change in frequency or the way that we hear sound is in pitch. So it's a change in frequency or pitch depending on whether or not the observer or the thing emitting the sound or light or whatever it is moving. Here we have an example of a fire truck. In the first thing on the left side here, it's stationary. The wavelength is the same in both the front and behind the truck as it's emitting. In the second situation on the, I think I said right before, it's on the left. Second situation on the right, it's now moving forward, so the truck is moving from left to right. The wavelength in the front of the truck, as the sound waves kind of build up, is smaller, and the wavelength in the back is wider. This means that you'll hear a higher pitch sound in the front and a lower pitch sound in the rear. This is kind of builds up to what we've seen with some of the things that we get to shock waves when we get to pressure and different things, or when we have more little applications to that. So it's the change in frequency, which is a change in pitch of sound, due to either a moving source or observer.
All right, so here's a kind of a little demonstration to show you what happens with the Doppler effect. So imagine we have some source, some person just kind of sitting right here, and boom. Here we have some source of sound, something that creates some disturbance in the air, a horn, anything like that. So there we go, and we get it to start moving, or not, it's just going to be stationary for now. And if we notice, sound waves are traveling out in all directions at the same speed, all directions, same speed. And since they're moving on a circular path, all the wavelengths between each crest is the same as they move out. So notice how out here, same wavelength as all the way in here. Now, stop that, and what I'm going to do is I'm going to set this moving so that the source of the sound is not quite moving. It's moving it right now, is what I'm going to say. It's going to move at half the speed. The source is moving at half the speed of the sound. So here we go, and if we notice here, we get this buildup of waves here in the front. And you see all these different waves here, so if we can kind of look there, the wavelength right there is smaller because the source is moving and emitting the sound. So once it emits the sound, it moves forward a little bit, moves forward with this, and then it kind of gets closer, and then emits another crest right there. So we have all these different crests where they're moving all right along here. And so here the wavelength is smaller, so that means an increase in frequency in front of it. And back here we have a bigger wavelength, and so there's a decrease in frequency. Now, if we get this to move at exactly the speed of sound, so if we get this to move at the speed of sound, we have right here, so it's moving at the speed, we get this bow wave right here where it's this build-up here. And this is kind of what we're going to start when we start talking about sonic booms, which you've already seen a little bit on. And we go along here with this, there's going to be a build-up of pressure right here, because if you kind of see this huge line right here. Back here, much lower pitch. That's the pitch, once again, is how we relate the frequency of sound to our ear, to what we hear. And now if we move faster than the speed of sound, Let's go 1.5 times the speed of sound. Just make it nice and simple. Moving right here. The source is moving faster than the sound waves. So this is how we get that shock wave coming out. This refers to the Mach number. So if you hear a plane doing Mach 2, it's going twice the speed of sound. All right, I hope this was a little bit more helpful in kind of seeing this visualization.
All right, one big kind of nasty looking equation in how to solve Doppler effect problems. And if we're going to go through and we're going to sort it out and kind of look it through each step. So first, we have frequency of the source, that's Fs. And second, we have frequency of the observer. Sometimes it's just written as F for the frequency of the source and F prime for frequency of the observer. V naught or VO depends on the velocity of the observer, where V refers to, that with no subscript, refers to the velocity of the wave itself. Vs stands for the velocity of the source. So let's look at first if the observer is stationary. If the observer is stationary, the velocity of the observer is 0, so the top part of this equation just becomes 1. If the source is stationary and the observer is moving, then the bottom part of this equation just becomes 1. So it's you have to kind of think about whether or not the source and the observer are moving, first off. Next, when the source is moving towards the observer, in the bottom part of the equation, the negative symbol is, the situation is negative, the velocity is negative when it's moving towards the observer. And the reverse happens when the observer is moving towards the source. This kind of makes sense if you think about the wave, so if they're kind of reversed. If the observer, is moving towards the source, then it's a positive, and this is for the top half of the equation. And if the source is moving towards the observer, it's the negative, and this is for the bottom half of the equation. And it's opposite when it's reversed. So if it's moving away if the observer is moving away from the source, then on the top half of the equation it's going to be negative. And if the source is moving away from the observer, again, on the bottom half of the equation it will be positive. I think that once we do a couple problems in class, this will become a little bit more straightforward and you'll be a little bit more comfortable with this. But just to understand, there's just one big formula for this, and we got to set it up for each situation. So it's important to read a question thoroughly for a situation. One of the most common Doppler effect applications is in weather, and I think you hear this all the time when they go, oh, let's go to our Doppler radar. And what happens is a radar sends out an electromagnetic wave in the range of an X-ray, and that X-ray travels and it bounces off some amount of precipitation, or what they call hydrometer or something like that, which just refers to rain or snow or anything like that. And then it returns to the source. And so this is how they're able to pick up where, based on how long it took that radio wave to come back, that electromagnetic wave to come back to the radar station, they can tell where this rain is. And they can also tell, based on this, how the storm is moving, based on the intensity, how much of the radio wave is reflected back, and how long it is, and different things like that. But this is used to detect weather movements with precipitation. They can use it for clouds too at higher altitudes. So they have different levels where they can go through and do this. And they also use this a lot with predicting how storms move. So with tornadoes and hurricanes, they can look at how you have something that's called a Doppler shift, where one side it's moving, if it's spinning, one side's really moving towards the observer and the other side's moving away. So you kind of get this a different effect there, which we'll talk a little bit more about in class, or maybe tomorrow in the next video. But so this is kind of the application of the Doppler effect in detecting storms and storm movement. All right, one sample problem for tonight. A rocket moves at a speed of 242 meters per second towards a stationary observer, while emitting sound waves at a frequency of 1,250 hertz. So right now we know that the source is moving and the observer is stationary, and the source is moving towards the observer. So we can already set up our equation in a certain way. If you go back and rewatch that part of the video, you can figure out how to set up the equation in order to solve for this. What frequency does the observer measure the sound to be at? You need to also know for this the speed of sound in air, which you can look up in your book. Assume it's 20 degrees Celsius, and we'll go from there. And second question, assuming this is traveling through air that is at room temperature, what is the wavelength of the emitted sound? So what is the wavelength of the emitted sound? Thank you very much. I hope you had a good video here, nice little quick lecture, and have a good night.